I forget what it is. It's 38 forks, and those are like directed studies that he throws out, and that was the spring. It was like going into oh, it's 3480. Yeah, 3480. And then this fall was like sustainable backyard gardening. That's right. I'm not gonna say this, but I don't know. That's right. It was like growing coffee, like chocolate, and then hops. Yeah, I saw that thing.
You guys had a lot of insect outbreaks up in Cloquet. Insect outbreaks up in Cloquet. Have you had nothing? But nothing.
I feel at times. That's probably
Yeah.
There's a way out of it.
I started doing stuff with, I tried to do another chronosequence with insect disease outbreaks up in Alaska, determining the time of the outbreak is somewhat problematic. And the trends compared to a harvest or forest fire are like much more minute, at least in some cases.
It gives us some directions, like we harvest that we use that to like no, for just like the final age and final height. Wow, just woke up.
Okay. Just a comment on the assignment. A number of people have already turned the assignment in, but if you are writing things out on paper, then what you'll need to do is either scan or take pictures, whatever. People have already done that. I looked at a few that people had submitted. That doesn't seem to be an issue, but I would just ask that you make sure that any images you submit are readable. That's your responsibility to make sure that things are readable when you submit them. Shouldn't be an issue, but just something I want to pay attention to. Okay, any questions? So exam next Wednesday. Doesn't cover today, doesn't cover Monday, covers through Wednesday. Two assignments. Okay. So, for this last third of the course, talking about stand dynamics, thus far we've considered two important factors controlling stand dynamics: what their impact is, how they affect stand dynamics, and how we go about quantifying them. What are those two factors? To review.
Site quality.
Site quality
And
stand density, absolutely. So where are we going with this? We're going to want to get an idea of the sorts of growth and yield models that are available to us for helping in silvicultural prescriptions, helping in management planning, harvest scheduling, and so forth. We're not going to get into the specifics of how these models are derived. We just want to know about the various types of models that are available, what their shortcomings are, what their advantages are, and so forth. So So before we get to the models, we need to understand basic tree growth patterns and stand growth patterns. So we'll spend the next couple of lectures or so talking about tree growth and then aggregates of trees, growth of stands. So we'll first look at individual tree growth. Now, for stands that are basically one age class, single age class stands, there is such a thing as an average tree in such stands. And the growth of that average tree tells us a lot about the growth of the stand. That's pretty convenient. Stand growth and individual tree growth pretty much parallel one another for single age class stands. For multi-age class stands, anything other than a single age class stand, things are much more complex because we have vertical stratification, horizontal stratification, and so forth. Trees maturing at different times, so forth and so on. So more complex, and therefore the models that we need for such stand conditions are going to be more complex. We'll focus most of our attention on single age class stands, just because it's simpler, and with that basic understanding we can extend some things to multi-age class. So what about individual tree growth? We're going to be mainly concerning ourselves with the growth of the bole. And in terms of growth of the bole, we'll think in terms of radial increment, diameter increment, and also height increment. And for trees growing in our parts of the world, as opposed to some other areas, trees grow up. Well, all trees grow up, right? But they grow from the top up, where we're at. So we're talking about apical growth. Well, you might say, well, that bole, that's only one part of the tree. Well, of course, from a timber management perspective, that's the most important part of the tree, at least from a utilization perspective. But certainly we need to recognize that there are other parts to trees, other compartments, as we would say when we're modeling them. Branches, foliage, roots, and so forth. We will assume that this idea of allometry holds for these different compartments. That is, we ought to see proportional growth for roots versus bole, for crown versus bole, and so forth. So, and of course this is pretty common because what sort of growth is easiest to observe, easiest to measure? The bole, right? I mean, the crown's out there, we can measure it, but measuring crowns more difficult, and crowns aren't, they can be very non-uniform, right? So difficult to characterize, and certainly roots, real issue there. So we're just going to assume that things are growing in proportion to one another. That's a very common idea that's used with biological organisms. So we'll focus on growth of the bole. So growth of the bole impacted by several factors, just like stand development. Age, number one. And we'll spend most of the rest of the time talking about patterns of growth over time for individual trees. But there are many other factors. Right? Genetic variability. Some species of trees are highly variable genetically. Some are not, like red pine, not very genetically diverse, but others are. So that's going to, aspen is an example, right? Are going to show great deviations based upon genetics from the overall basic age-size relationship. Site resources, just as we talked about at the stand level. Site resources available to the individual tree. So it's how much resource is the site going to make available, and then how much competition is that tree going to undergo for utilization of those site resources. So it's not surprising that those two factors show up again. More on the stochastic end of things, pathogens, insect disease, that's going to impact tree growth, boll increment, and there are many others, weather, variation, annual variation in weather, trends in climate, so forth. So, pretty complex. And yet, we need to understand it. We need to develop models that give us a basic idea of how these trees are developing. And you can see, therefore, that these models, well, like people usually say, models are always wrong, right? It's whether they're useful or not that we want to evaluate. So we know that we're up against an extremely difficult task, but we'll try to come up with usable models. We can come up with really complex models that take into account a lot of these factors, even the stochastic ones, right? But they're not going to be usable by forest managers, by silviculturalists, and so forth. So we want models that are usable and do a halfway decent job of taking care of, or taking into account these various factors and impact increment. Okay, so what about this basic pattern of growth? So here's what it looks like for trees. Same thing as what it looks like for humans. Any biological organism has this basic S-shaped growth curve, sigmoidal shaped growth curve, where we have some measure of size on the vertical axis and time on the horizontal axis. And it's common to divide that sigmoidal growth curve into three phases. And they're labeled here: the youth phase, the maturing phase, and then the senescing phase. The transition between youth and maturity is pretty well defined. We get this youth phase transitioning into maturity. The transition there is where growth goes from increasing at an increasing rate to increasing at a decreasing rate. So still increasing, right? But it's increasing at a decreasing rate. That has a name in mathematics, calculus. Anybody had calculus and remember what that point is called? Inflection. Inflection point. That's the inflection point. So we can find that point mathematically. What do I mean, find that point? Find the age or the time of the transition from increasing at an tree growth increasing at an increasing rate to increasing at a decreasing rate. Not so clear on the transition between maturing and senescing. Some people would define that as the time where mean annual increment is a maximum. And that basically corresponds to, and it doesn't show on here, that basically corresponds to a point where I stick this at 0 and wherever it's tangent to this curve. Many people will take that as the transition from maturing to senescing. Because we know at the stand level, at least from forest management, that age of maximum mean annual increment is the point at which we maximize a perpetuity of yields. It's the same it holds for individual trees. So we could play with these ideas in all sorts of packages, but in Wolfram Alpha. So here's a graph of a particular function that will give us that sigmoidal shape. Not linear, right? You can't just use a straight linear equation. That's not going to work. So here we're saying size is this particular function of age or of time. So if we want to find this inflection point,